Scaling laws are critical in science and engineering because they reveal how physical systems behave as their size changes, offering predictive power for designing and understanding various systems. For instance, in structural engineering, the strength of a beam scales with its cross-sectional area, while its weight scales with its volume, meaning larger beams may require disproportionate reinforcement. In biology, scaling laws explain why small animals like mice have faster heart rates than larger animals like elephants. Metabolism scales with body size. In aerodynamics, the drag on an object increases with the square of its velocity, influencing how airplanes and cars are designed for efficiency at different speeds. In nanotechnology, surface area to volume ratios become dominant at small scales, affecting reactions and properties like adhesion and heat dissipation. By applying these principles, scientists and engineers can optimize designs from skyscrapers to microchips and understand phenomena across scales from galaxies to molecules.
Nature inherently obeys scaling laws, which manifest in phenomena like metabolic rates, fractal patterns in ecosystems, and growth laws in organisms. For example, Kleiber's law states that an organism's metabolic rate scales to the 3/4 power of its mass, reflecting constraints imposed by the geometry of vascular systems and energy efficiency. In materials science, the Hall-Petch relationship describes how the yield strength of metals increases inversely with the square root of grain size, underpinning strategies to design stronger materials. Technological advancements leverage scaling laws to innovate. In electronics, Moore's law, a practical scaling law, predicts the exponential increase in transistor density, enabling rapid miniaturization and performance improvement in computing devices. However, as transistors approach atomic scales, quantum effects challenge the continuation of this trend, demanding novel paradigms like quantum computing or neuromorphic systems. Example: in nanotechnology, surface forces become dominant over volume forces as dimensions shrink. This is why nanoparticles exhibit high surface energy and unique properties like enhanced catalytic activity or superhydrophobicity. This scaling effect drives applications from drug delivery to energy storage. Analogy: scaling in engineering is like changing the size of a recipe. Doubling the ingredients ensures the taste remains consistent, but the cooking time may change due to different heat dynamics in a larger volume. Similarly, scaling physical systems requires understanding how certain parameters change while maintaining system functionality. Scaling laws are mathematical relationships that describe how physical properties change with size, shape, or other parameters. These laws are ubiquitous in science and engineering, providing a framework to understand phenomena across scales, from the microscopic to the macroscopic. The principle of scaling often involves dimensional analysis, where physical quantities are expressed in terms of fundamental units, e.g., length, mass, time, to reveal underlying proportions. Similarly, in structural engineering, the strength of a beam scales with its cross-sectional area, while its weight scales with its volume, influencing design decisions for bridges and buildings. In nanotechnology, scaling laws explain why materials at the nanoscale exhibit properties, e.g., higher strength, increased reactivity, distinct from their bulk counterparts. Dimensional analysis is a mathematical technique used to derive relationships between physical quantities by examining their dimensions, e.g., length, mass, time. It ensures that equations are dimensionally consistent and reveals how different quantities scale with each other. The Reynolds number in fluid dynamics is a dimensionless quantity derived through dimensional analysis. It compares inertial forces to viscous forces in a fluid flow. This analysis helps predict whether the flow will be laminar, smooth, or turbulent, chaotic. The result is scale-independent, meaning it applies universally across different sizes and types of systems. Dimensional analysis is widely used in engineering, physics, and chemistry to simplify complex problems. It allows researchers to predict system behavior without detailed numerical solutions, such as determining the efficiency of a wind turbine based on its size and wind speed. Scaling laws in reaction rates on different scales. Catalysis is the acceleration of chemical reactions by substances, catalysts, that are not consumed during the reaction. The effectiveness of a catalyst often depends on its surface area relative to its volume, as reactions typically occur on the surface. Smaller particles or nanostructured catalysts provide more surface area for reactions, making them more efficient. Detailed example. Consider a metal catalyst like platinum used in car exhaust systems to convert harmful gases into less toxic substances. Nanoscale platinum particles have a much higher surface area than larger particles, enabling more catalytic sites for reactions like the breakdown of carbon monoxide. This increased surface area makes nanoscale catalysts far more efficient than bulk materials. Implications. Scaling down catalysts to the nanoscale is critical for industries such as petrochemical refining and green energy, where high efficiency and low material usage are essential. It also plays a role in designing catalysts for hydrogen production and storage. Scaling laws in structural models and stress analysis. Civil engineering involves designing and analyzing large structures like buildings, bridges, and dams. Scaling laws help predict how these structures will behave as their size changes. Stress and strain in a structure depend on its shape, material properties, and external forces. Detailed example. When scaling a model bridge for wind tunnel testing, the forces acting on the structure must scale correctly to simulate real-world conditions. For instance, the strength of materials in the model must accurately reflect the behavior of materials in the full-scale structure. Failure to account for these scaling laws can lead to design flaws, as the structural integrity may not scale linearly with size. Implications. Understanding these principles is crucial when testing scaled-down models of skyscrapers or dams, as the behavior of stresses and vibrations in the model must represent real-world scenarios to avoid catastrophic failures. Fractals are mathematical objects with self-similarity, meaning their structure looks similar at any scale. This makes them ideal for describing natural phenomena like coastlines, clouds, and plant growth. Consider the Mandelbrot set, a famous fractal. Zooming in on the set reveals intricate details that mirror the overall shape. The complexity increases as you zoom further, but the same fundamental patterns recur at smaller scales. This self-similar behavior is governed by scaling laws, where the same geometric or functional rules apply regardless of the magnification. These scaling laws allow fractals to maintain their structure at any level of zoom, demonstrating their inherent recursive properties. Fractals have practical applications in fields like computer graphics, e.g., generating realistic landscapes, and biology, e.g., modeling vascular systems or lung structures. Chaos theory, a closely related concept, explores how small changes in initial conditions can lead to vastly different outcomes, as seen in weather systems or financial markets. In mechanics, scaling laws reveal how size affects an object's strength, weight, and structural stability. When objects grow larger, their weight increases much faster than their ability to support themselves. Weight is proportional to the object's volume, while strength depends on the cross-sectional area of the material that resists force. This mismatch explains why larger objects or structures are more prone to failure unless specifically engineered. Consider a wooden beam used in construction. If the length of the beam is doubled, its volume and weight will increase 8 times because volume scales with the cube of size. However, its strength only increases 4 times because strength scales with the square of size. This discrepancy means that a longer beam is more likely to break under its own weight unless reinforced. This principle explains why large buildings, such as skyscrapers, require advanced engineering techniques like steel reinforcements, whereas small structures can often stand with minimal support. It also underlies why smaller creatures, like insects, can survive falls from great heights, as their mass is too small to generate dangerous impact forces. Scaling of device performance at the nanoscale. Nanofabrication involves creating structures and devices at dimensions below 100 nanometers. At this scale, material properties and device performance are dominated by surface effects, quantum phenomena, and other non-classical behaviors. Detailed example. In the fabrication of transistors for microchips, shrinking the size of components reduces the distance that electrons travel, which increases speed and reduces power consumption. However, as transistors approach the nanoscale, new challenges like quantum tunneling arise, where electrons can leak through insulating layers. Implications. Scaling in nanofabrication has driven the miniaturization of electronics, enabling devices like smartphones and laptops to become more powerful. However, engineers face trade-offs, as smaller devices may also exhibit increased heat generation and reliability issues, requiring innovative materials and designs. The surface area to volume ratio governs many physical, chemical, and biological processes, dictating how efficiently a system can exchange heat, nutrients, gases, or waste. As an object's size increases, its surface area scales with the square of its dimensions, while volume scales with the cube. This disparity becomes critical at smaller scales, where surface phenomena dominate. Biological systems, for example, evolve adaptations like villi in the intestines or alveoli in the lungs to maximize surface area for efficient exchange. Engineering designs mimic this principle in heat exchangers and catalytic converters. Example: bacteria are small to maximize their surface area relative to their volume, allowing for rapid nutrient absorption and waste excretion. In contrast, larger animals like elephants must rely on specialized structures like large ears to dissipate heat. Electromagnetic scaling laws describe how electric and magnetic forces change with distance and charge distribution. Electric fields, for example, weaken as you move farther from the source. The strength of these fields depends on both the amount of charge producing them and the geometry of the system. Imagine you're holding a magnet and moving it farther from a metal object. The magnetic force becomes weaker the farther you move because the influence of the magnet spreads out over a larger area. Similarly, the design of electrical devices like antennas or transformers must account for how fields diminish with distance to optimize efficiency. This scaling governs the performance of everything from power lines to wireless communication. It also explains why high-voltage electricity is used to transmit power over long distances. By reducing current, it minimizes energy losses caused by resistance in the wires. Scaling laws in machines and components. In mechanical engineering, scaling affects the performance of machines and their components. The forces, power output, and heat generation of machines change with their size, requiring careful design modifications for efficiency and durability. Detailed example. A small engine is more efficient relative to its size than a larger one because heat loss scales with surface area, while energy production scales with volume. However, larger engines can handle more power output due to their increased mass, provided they are adequately cooled. Implications. This understanding is vital for designing vehicles, robots, and industrial machinery. For example, miniaturizing gears for wristwatches requires attention to material strength and friction at tiny scales, which behave differently than in larger gears. At the nanoscale, quantum effects like energy quantization, tunneling, and electron confinement become significant. These effects dramatically alter the electronic, optical, and magnetic properties of materials, leading to phenomena that are not observed at larger scales. Quantum dots, which are nanoscale semiconductor particles, exhibit size-dependent optical properties. Smaller quantum dots emit blue light, while larger ones emit red. This is due to quantum confinement, where the movement of electrons and holes is restricted, leading to discrete energy levels. Quantum effects are critical for designing advanced materials and devices, such as efficient solar cells, high-resolution displays, and quantum computers. For example, the tunable light emission of quantum dots has enabled significant advancements in LED and display technologies. The Reynolds number, Re, represents the ratio of inertial forces to viscous forces in a fluid and determines the transition between laminar and turbulent flow. It is given by R equal V LRE equals frac rho VL, where rho R is fluid density, VVV is velocity, L is characteristic length, and mMo is dynamic viscosity. At low Re, viscous forces dominate, resulting in smooth flow, while high Re favors chaotic, turbulent behavior. Scaling effects make turbulence more prominent in larger or faster systems, crucial in aerodynamics, pipe design, and weather modeling. Example: airplane wings operate at high Reynolds numbers to manage turbulence and maximize lift, while microfluidic devices operate at low Reynolds numbers, ensuring laminar flow for precise control. Scaling laws also influence interdisciplinary fields, such as ecological modeling, urban planning, and cosmology. In ecology, allometric scaling describes relationships like population density and species diversity, providing insights into resource distribution and conservation strategies. In urban studies, Zipf's law and the scaling of infrastructure networks reveal patterns in city growth and resource allocation. Cosmologically, the scaling of gravitational forces with mass and distance governs the structure of galaxies and the dynamics of the universe. Scaling laws in adsorption on micro versus nanoscales. Surface chemistry focuses on interactions occurring at the surface of materials. Adsorption, the process by which molecules adhere to a surface, becomes more pronounced at smaller scales due to the increased surface area to volume ratio of nanoparticles. Detailed example: activated carbon, used in water purification, adsorbs pollutants due to its high surface area. If the activated carbon particles are further reduced to the nanoscale, their adsorption capacity increases significantly, allowing more contaminants to be removed with less material. Implications: this scaling principle is vital in fields like catalysis, environmental science, and drug delivery. For example, nanoscale particles can adsorb more active drug molecules, making drug delivery systems more efficient and targeted. In aerospace engineering, the behavior of aircraft and spacecraft is governed by the interplay of forces such as lift, drag, and thrust, which scale differently with size, speed, and altitude. Large airplanes need disproportionately larger wings compared to small ones because lift depends on the surface area of the wings. Similarly, drag forces increase dramatically with the size and speed of the aircraft, requiring more powerful engines to achieve flight. These principles explain why drones and small aircraft are much easier to design than large commercial jets or spacecraft. Engineers also use scaled-down models in wind tunnels to study aerodynamics, ensuring the results accurately predict full-scale behavior. Fluid dynamics scaling laws explain how fluids behave depending on the size, speed, and viscosity of the system. The Reynolds number, a critical concept, determines whether a fluid's motion is smooth, laminar, or chaotic, turbulent. This dimensionless number compares inertial forces, causing motion, to viscous forces, resisting motion. Detailed example: water flowing through a narrow pipe at a slow speed exhibits smooth, predictable motion. This is because the viscous forces dominate, keeping the flow orderly. However, if the pipe is widened or the water moves faster, the flow becomes turbulent, creating whirlpools and eddies. Engineers use these principles to design pipelines, aircraft, and even the cooling systems in computers. Implications: understanding fluid dynamic scaling is crucial for designing vehicles, e.g. reducing drag on airplanes, predicting weather patterns, and creating medical devices like blood flow monitors. Small-scale systems, such as microfluidic devices, often rely on laminar flow for precision control of fluids. Kleiber's law states that an organism's metabolic rate R scales as R m's core 3-fold, where m is the body mass. This allometric scaling arises from the geometry and fractal nature of biological transport systems like circulatory networks, which must distribute resources efficiently. Larger organisms have lower metabolic rates per unit mass, conserving energy, while smaller organisms require higher rates to sustain their fast metabolisms. This scaling principle explains patterns in energy consumption, growth, and reproduction across species. Example: hummingbirds consume more energy per gram of body weight than elephants because their metabolic systems must sustain rapid movements and high energy demands. Energy and force scaling nanomotors and nanomachines operate at scales where surface forces, thermal fluctuations, and quantum effects dominate over classical forces like gravity or inertia. Energy input and force output scale differently compared to macroscopic machines. Detailed example. A catalytic nanomotor, such as one powered by chemical reactions, e.g. hydrogen peroxide decomposition, generates motion by exploiting surface chemistry. At the nanoscale, surface-to-volume ratios are extremely high, meaning surface interactions, e.g. catalysis, play a much larger role in energy conversion than they do in larger machines. Implications. These scaling principles are essential for applications in targeted drug delivery, environmental sensing, and microscale assembly lines. Nanomachines must be designed to harness forces like van der Waals interactions and thermal energy, which become dominant at this scale. Scaling laws in quantum effects at small scales. At the nanoscale, quantum effects dominate the behavior of materials, resulting in properties that differ significantly from their bulk counterparts. Quantum confinement, for example, occurs when the size of a particle becomes comparable to the wavelength of an electron, leading to discrete energy levels. Quantum dots, tiny semiconductor particles, exhibit unique optical properties such as size-dependent fluorescence. Smaller quantum dots emit blue light, while larger ones emit red light, making them useful in applications like high-resolution displays and medical imaging. These scaling laws enable the development of advanced nanomaterials with tailored properties for electronics, photonics, and medicine. For instance, nanoparticles are used in cancer therapy for targeted drug delivery, exploiting their unique ability. Scaling laws in the miniaturization of circuits. In electrical engineering, scaling laws guide the design of smaller and more efficient electronic devices. As components are miniaturized, their electrical properties, such as resistance, capacitance, and inductance, change, often introducing quantum effects. Detailed example. In microchips, as transistors shrink, the distance that electrons must travel becomes smaller, reducing resistance and improving performance. However, at extremely small scales, quantum tunneling can cause electrons to leak across insulating barriers, leading to power loss and heat generation. Implications. Understanding these scaling effects has driven innovations like multi-core processors and 3D chip designs, which help overcome the limitations of miniaturization. It is also crucial in designing energy-efficient devices, such as smartphones and wearable technology. Scaling laws in molecular weights. In polymer science, the physical and chemical properties of polymers depend on their molecular weight, which is a measure of the size of the polymer chains. As molecular weight increases, properties like strength, elasticity, and viscosity also change. Detailed example. Low molecular weight polymers, like those used in adhesives, are soft and flow easily, whereas high molecular weight polymers, like those used in bulletproof vests, e.g. Kevlar, are incredibly strong and rigid. The relationship between molecular weight and properties is nonlinear. Doubling the molecular weight can lead to disproportionately large increases in strength or viscosity. Implications. This scaling law is critical in tailoring polymers for specific applications. For instance, lightweight and flexible polymers are used in packaging, while high-strength polymers are essential in aerospace and defense industries. The relationship between strength and weight in structures is influenced by how these properties change as size increases. Strength depends on the cross-sectional area of the structure, which grows at a slower rate compared to weight, which is determined by the overall volume. This principle is observed across various fields, such as biology, architecture, and materials science. It explains why larger objects or organisms require additional support to remain stable and functional. In bridge construction, longer spans mean heavier overall weight. To ensure stability, engineers design supports to be thicker or stronger to handle the increased load. Without these adjustments, the bridge could collapse under its own weight. Large animals, like elephants, have much thicker and sturdier legs compared to smaller animals, such as cats. This adaptation is necessary because their weight grows disproportionately compared to their bone strength, requiring additional support to prevent collapse. By understanding this scaling effect, engineers and scientists can design structures, materials, and even biological systems to withstand the stresses of increased size, ensuring safety, functionality, and longevity. In thermodynamics, scaling laws govern how heat moves through materials. Smaller objects, due to their higher surface area relative to volume, lose heat more quickly than larger ones. This phenomenon is a direct consequence of how surface area scales with size compared to volume. A small ice cube melts much faster than a large block of ice. A small ice cube melts much faster than a large block of ice because the cube's surface area where heat exchange occurs is much larger relative to its volume. Conversely, large animals like elephants have more difficulty dissipating heat than small animals like mice, which is why elephants rely on adaptations like large ears to help cool their bodies. These scaling laws are critical in fields like materials science and engineering, where heat transfer efficiency impacts the design of engines, electronics, and insulation systems. It also explains why houses lose heat faster when poorly insulated, as heat escapes through the large surface areas of walls and windows. Scaling laws in reactor design and diffusion processes. Chemical engineers must scale up processes from laboratory experiments to industrial reactors while ensuring efficiency and safety. Scaling laws govern heat transfer, chemical reaction rates, and diffusion, which often behave non-linearly as systems grow. Detailed example. In a chemical reactor, the reaction rate depends on the surface area of the catalyst and the volume of reactants. When scaling up, the surface area increases slower than the volume, leading to inefficiencies if not addressed. Additionally, heat generated in reactions must be dissipated efficiently, which becomes more challenging in larger systems. Implications. These principles are critical for designing efficient industrial reactors for processes like petrochemical refining or pharmaceutical manufacturing. These principles are critical for designing efficient industrial reactors for processes like petrochemical refining or pharmaceutical manufacturing. Engineers must optimize heat exchangers, mixers, and catalysts to ensure the process scales effectively. Fractals are self-similar structures, meaning their patterns repeat across scales. This property is seen in natural systems like river networks, lung structures, and lightning strikes. Fractal scaling optimizes functions like nutrient transport, energy dissipation, and surface area maximization. The mathematical scaling laws governing fractals reveal how systems achieve efficiency and resilience through repeating geometric patterns. An example of fractal scaling is the branching of blood vessels in humans, ensuring efficient delivery of oxygen and nutrients to tissues while minimizing energy expenditure. At the nanoscale, classical mechanics breaks down and quantum effects dominate. Properties like energy levels, charge transport, and optical behavior scale with particle size and shape. Quantum confinement occurs when particle dimensions are comparable to the electron's de Broglie wavelength, altering its energy states and interactions. These quantum effects drive innovations in nanotechnology, semiconductors, and materials science. For example, quantum dots emit light at specific wavelengths based on their size, enabling applications in displays, imaging, and photovoltaics. The square cube law states that as an object's dimensions increase, its surface area scales as L2, while its volume scales as L3. This disproportionate scaling affects biomechanics, heat dissipation, and metabolic rates. Larger organisms must develop adaptations to manage the structural and physiological constraints imposed by this law. For example, birds have hollow bones to reduce weight while maintaining strength, a necessary adaptation for flight under the square cube scaling constraints. Quantum mechanics describes phenomena that only become apparent at very small scales, where the rules of classical physics break down. At these scales, energy, motion, and even the position of particles are quantized, meaning they take on discrete rather than continuous values. Detailed example. In quantum tunneling, particles like electrons can pass through barriers that classical physics says they shouldn't be able to cross. This effect is crucial in modern technology, such as the operation of transistors in computer chips. Similarly, the behavior of light at the quantum level enables technologies like lasers and quantum cryptography. Implications: as objects become larger, the quantum effects become negligible, and classical physics dominates. For example, while electrons in a semiconductor exhibit quantum behavior, a baseball, composed of many atoms, behaves entirely according to classical mechanics. This scaling law is essential for fields like nanotechnology and quantum computing. In astrophysics, scaling laws describe how gravitational forces behave at large scales. Gravity's strength increases with the mass of the objects involved and decreases as the distance between them grows. These laws govern the motion of planets, the formation of stars, and the behavior of galaxies. Detailed example. Planets orbit stars in predictable patterns because of gravitational forces. The closer a planet is to its star, the stronger the gravitational pull, and the faster the planet must move to stay in orbit. In larger systems like galaxies, the combined gravitational pull of billions of stars holds the galaxy together, even as it rotates. Implications: scaling laws in gravity help explain phenomena like black holes, where gravity becomes extremely strong due to the immense concentration of mass, and why stars and planets form spherical shapes. These laws are fundamental to understanding the structure and evolution of the universe, from small planetary systems to massive galaxy clusters. Scaling laws in nanomechanics, thin films, and coatings. Materials engineering deals with how materials behave at different scales. When materials are reduced to nanoscale dimensions, their properties, such as strength, conductivity, and optical behavior, change dramatically. Detailed example. A thin film of material, such as those used in solar panels or computer screens, has a much higher surface area relative to its volume. This makes it more susceptible to surface defects, which can significantly affect its strength or conductivity. Similarly, nanomaterials like carbon nanotubes exhibit much greater strength and flexibility than their bulk counterparts due to quantum and surface effects. Implications: these scaling effects are crucial in industries like electronics, renewable energy, and medicine. For instance, nanocoatings are used to make surfaces hydrophobic or antimicrobial, while thin films enable the production of flexible electronics and high-efficiency solar cells. Heat transfer in systems depends on conduction, convection, and radiation, each scaling differently with size and temperature. Conduction scales with cross-sectional area and temperature gradient, while convection depends on surface area and fluid dynamics. Radiation, governed by the Stefan-Boltzmann law, scales with the fourth power of temperature, making it dominant at high temperatures. Example: insulation in homes minimizes heat loss through conduction and convection, but radiation becomes significant at extreme temperatures, such as in spacecraft design. Cells rely on diffusion for transport processes, but diffusion efficiency scales with the square of the distance, TD square. This quadratic relationship limits the size of cells, necessitating multicellularity and specialized transport systems in larger organisms. Scaling also influences cellular shapes and structures to optimize exchange. Example: nerve cells develop long, thin axons to rapidly transmit signals while minimizing the limitations imposed by diffusion scaling. Elastic deformation in materials scales with stress, which is proportional to applied force and inversely proportional to cross-sectional area. Larger systems face greater challenges in maintaining structural integrity under scaling effects, leading to innovative designs for stability and elasticity. In energy systems, storage capacity typically scales with volume, while power delivery scales with surface area. This difference influences the efficiency and scalability of batteries, fuel cells, and capacitors. Nanostructured materials improve performance by increasing reactive surface areas. Supercapacitors use nanomaterials to achieve high power density and fast charging, leveraging surface area scaling. Urban scaling laws show that infrastructure and resource use scale sublinearly with population, reflecting economies of scale. Larger cities become more efficient, consuming less energy per capita while increasing innovation and economic activity. However, they also face challenges like congestion and inequality. Tokyo's dense infrastructure optimizes public transportation and energy use, exemplifying urban scaling efficiencies. Wave behavior, such as speed and attenuation, scales with system size, material properties, and wavelength. Shorter wavelengths enable higher resolution and precision, influencing fields like optics and acoustics. High-frequency ultrasound uses short wavelengths to achieve detailed imaging in medical diagnostics. Allometric scaling describes how biological traits, e.g., metabolism, lifespan, population density, scale predictably with size. It reflects energy constraints and resource allocation across ecosystems. For instance, larger animals require more resources but process energy more efficiently due to metabolic scaling M34. Similarly, population density in ecosystems often decreases as organism size increases, ensuring resource balance. In forests, the density of small insects is far higher than the density of large mammals like deer, reflecting energy and space constraints governed by allometric scaling. Diffusion in fluids or gases scales with distance squared, T is d squared, where T is time and d is distance. At small scales, diffusion dominates, enabling passive mixing and molecular transport. However, as scales increase, active transport mechanisms become necessary to overcome the inefficiency of diffusion. This principle influences designs in microfluidics, chemical reactors, and biological systems. In microfluidic devices, diffusion rapidly mixes chemicals in narrow channels, while larger reactors require mechanical stirring to achieve uniformity. Gravitational forces scale inversely with the square of the distance between two masses, F1r², governing planetary orbits, tidal forces, and galaxy dynamics. At larger scales, gravity dominates other forces, while at smaller scales, electromagnetic and nuclear forces become significant. The interplay of gravitational scaling and other forces shapes the universe's structure. The formation of spherical planets occurs because gravity scales uniformly in all directions, pulling matter toward the center. The natural frequency of an object scales inversely with its size and mass. Vibrational energy distributes differently based on object dimensions, influencing the design of resonators, musical instruments, and seismic detectors. Smaller objects vibrate at higher frequencies, while larger ones have lower natural frequencies. A violin string vibrates faster, producing higher pitch than a double bass string due to differences in length, tension, and mass. Turbulent flow involves energy transfer across scales, from large eddies to smaller ones, governed by Kolmogorov's scaling laws. The energy dissipation rate depends on viscosity and the size of the smallest eddies, leading to complex behaviors in large-scale systems like rivers or atmospheric currents. Understanding turbulent scaling is vital for efficient designs in transportation, energy, and environmental engineering. Aircraft wings are designed to control turbulence, minimizing drag and maximizing lift based on the scaling laws of fluid dynamics. In structural engineering, weight scales with volume L3, while strength scales with cross-sectional area L2. This mismatch imposes limits on the size and shape of buildings, bridges, and towers. Material innovations like composites and lattice designs help engineers overcome scaling constraints. The Eiffel Tower's truss structure optimizes weight distribution, ensuring stability despite its towering height by adhering to scaling principles. In aerodynamics, lift and drag forces scale with surface area, L2, and velocity squared, V2. This scaling governs the efficiency and stability of flight systems, requiring careful balance to maintain control at different speeds and sizes. Modern drones are small and lightweight to minimize drag and achieve greater maneuverability, while large aircraft use streamlined designs to balance lift and drag forces. The probability of quantum tunneling, where particles pass through energy barriers, scales exponentially with barrier width and height. This scaling governs phenomena in nanoscale devices and quantum computing, where precise control of barrier properties enables functional behavior. In transistors, electrons tunnel through barriers to switch states, enabling miniaturized electronics critical for modern computing. The resolution of optical systems depends on the wavelength of light and aperture size. Resolution scales inversely with wavelength, meaning shorter wavelengths provide finer details. This principle underpins technologies like electron microscopy and X-ray imaging, enabling visualization at nanoscale resolutions. X-ray crystallography uses short wavelengths to determine the atomic structure of proteins far beyond the resolution of visible light. In hydraulic systems, force scales with the cross-sectional area of the piston. F is proportional to A, while pressure remains constant throughout the system. This scaling allows small input forces to generate large output forces, enabling applications like lifts and presses. A car hydraulic lift uses a small piston to apply force, magnified at a larger piston to lift heavy vehicles, relying on the principles of Pascal's law. Zipf's law describes how rank and frequency in systems scale inversely, forming a predictable distribution. It applies to phenomena like city populations, word usage, and wealth distributions, highlighting scaling in complex systems. The most populous city in a country is roughly twice as large as the second most populous city, consistent with Zipf's law. In renewable energy systems, power generation scales with the area exposed to energy sources, such as solar panels and wind turbines. However, efficiency losses and material constraints impose limits on scalability. Wind turbines with larger blades capture more energy, but their size is constrained by material stresses and environmental factors, balancing efficiency with durability.